So, Chinenye, I can see that more and more people are joining, but we can start now and they
Okay.
can join us from there.
Okay. Good afternoon, everybody. Welcome to the next series, our webinar series, which we're doing for sub-Saharan African clients. And today we're going to be talking about the SCAL workflow, focusing on, generation of the simulation saturation table and using Techlog. So today, myself and Samuel are going to take you through this presentation. The agenda for today, we're going to look at a brief introduction of core analysis and the different methods available. We'll look at the importance of special core analysis, look at the workflows available in Techlog for saturation function table generation, and then we're going to have some demo sessions and conclude the presentation. Like we all know, most of us here are familiar with core analysis, which is the laboratory study of reservoir rocks that we take when we're drilling or after drilling. And there are two broad classifications of how core analysis or the lab studies are carried out. One is the conventional core analysis or the routine core analysis, where we obtain basic measurements such as the permeability, porosity, the fluid saturation, the grain density, and the core gamma log. The second method, which is the focus for today, is the special core analysis, which is basically a measurement of two-phase flow or sometimes three-phase flow. And then we just flow experiments are conducted, on those core plugs that we take to measure the relative permeability, the capillary pressure, wettability, and then the electrical properties of the plug. Now, why is core and SCAL or special core analysis important? It's important to both like the asset team, like the geologist, petrophysicist, and the reservoir engineer, particularly because for the geologist, it helps in terms of the volumes, what is available for us for the static model. And then from the static model, the reservoir engineer is able to initialize the simulation model and then come up with the production profile. So it's a key or a critical parameter that is very important to all the domains in the asset team. Now, how do we generate our SCAL saturation function tables? There are different approaches that are available industry-wide, but today we're going to focus on 4 different approaches available on Techlog. The first approach is the averaging of the relative permeability and the capillary pressure curves using the rock types. The second approach we'll be looking at is when we use correlations, the LET or the correlation, based on the endpoints that we get from our routine core analysis. The third approach we're going to be looking at is the capillary pressure and relative permeability curve based on a saturation height model. This is the binning approach. And then lastly, we're going to consider the parameter-based SCAL or special core analysis approach in Techlog. So at this point, I'll pass it on to Samuel, who is going to take us through some of the approaches, and then he would round up the presentation. Thank you.
Thanks, Chinenye. And again, good morning, good afternoon, good evening, everyone, depending on where you're joining from. I will start by laying the foundation of the importance that Chinenye just talked about of the relative permeability as essential input for understanding the multiphase flow in porous media and in describing the fluid contents in the reservoir. That is for the initialization and the subsequent dynamic behavior of the fluid flow in the reservoir simulators. These flow properties that we are talking about, they are represented as saturation functions, and that is why we're focusing on how to generate the saturation function or tables and give to the simulator. The first technique will focus on generating saturation function curves from the set of KRPC curves. So maybe from a special core analysis lab experiments on these several core samples, you have the relative permeability and capillary pressure. Now you want to kind of average this to reduce the number of the curves that you have to represent the similar rock types to the number that really makes good engineering sense. And this particular method, starts with the rock typing, and you guide your rock typing by, let's say, the pore fruit radius method. So there are several of such, and the approaches like using the quality index, the porosity. I mean, these are some of the approaches that we've got in Techlog that we can actually use. If I zoom out, the reservoir quality index, the zone flow indicator, the R35 Winland, and so on and so forth. So the reason for this is you want to know which rock type that each of these curves will belong to. Then you can separate them, then you can average thereafter. So that is the first step. The next step will be to convert the lab data that you've got into the reservoir conditions. So you're moving it from the lab conditions to the reservoir conditions. However, depending on the, let's say, capillary pressure that you've got, if it is coming from, let's say, mercury injection experiments, then there will be a need for the closure and the clay band water corrections prior to the conversion and the capping. The capping of the capillary pressure is also very, very important because that will really determine what the irreducible water saturation will be at the end of the day. Bear in mind that when the experiment was performed in the lab, they're looking at the entire core fruits. So imagine pumping the mercury, for instance, into the dry core to displace the wetting phase that was in the core. They will get the entire description of the capillary behavior, but the reality will set in based on the height of your reservoir. So your irreducible saturation will have to be defined on the basis of the capping. And that is why the step is very important. Then the next step, once you have done that, is to move on to the averaging capillary pressure data that you've got. Depending on how many rock types that you eventually identify, then you do averaging of your capillary pressure. And once that is done, then you move on to do the relative permeability averaging as well. One thing about the relative permeability in Techlog is, if you look at the table, the critical water saturation is actually defaulted to coordinate water saturation. So they're basically the same value, but you can adjust it. So the flexibility is there. When we go through the demo, I will show you how to do that. Next is the generation of the table. You can actually generate the table for family 1, family 2 keyword, or if you're using intercept, you can also generate the nodes that you need for the intercept. There are other options on the table generation window that you can set, like the precision, like the number of points. So one thing that I would need to mention before we move on this slide is the fact that by the time you have the average relative permeability curves and the average capillary pressure curves, the SWL in the relative permeability curve is definitely renormalized to match the SWL in the capillary pressure curve that you've got. So that is key. So let's look at how this is done in Techlog. So I'm going to put on the assumption that will help anybody, even if you have not used Techlog before, to be able to follow. And I will strongly encourage you to at least lay your hands on Techlog. Very powerful application and very easy to use. Well, I just launched a new Techlog application and I'm giving the name. So I'm going to call it SCAL Workshop for ARI or something like this. You set the project location where you want and you can create the project. I have existing projects, so I'm going to close that because I want to start with a new Techlog project. So the plugin, yes. But now this is a new Techlog project. There is no data in it if you look at the project browser. So what I'm going to do at this level is to go to the SCAL tab, as you can see, and try to import the Excel from the utility group into Techlog. And the Excel will be my relative permeability, my capillary pressure data that I've got from the lab, which I'm intending or planning to average. So when you click on the import, then the import window comes up. So I just want to show you what I'm about to import so that you see the files before bringing them into Techlog. So here is the relative permeability. You can see the depth for the sample. You can see the well name. You can see the porosity of that core and the permeability. And you can see for different core samples, basically. So I'm going to close that. And I also have the capillary pressure. So deliberately, here we have 3-phase system that we've created so that will show you the entire workflow of how to do that. That's the capillary pressure. Again, for the gas oil system, we have the relative permeability curves. What I'm going to do is to move this into Techlog. So very easy step. You can drag it or you can select the file, as the case may be. Just make sure that you're using import from Excel. So now you see the number of the core samples. You can actually go through them and see different data. So what I'm trying to do now is to set up the variables that we need there. The well name, that is a C2. Then I'm typing the data set name, whatever name that I want to call the relative permeability, whatever you intend to call it. So next, you want to fill the variables to import in. The name, that will be B2. You just drop in, drag and drop, very easy. The value of the depth will actually be C3. So you can also type the units. You're also going to set up the scheme for the table itself. So the value from line B6 to B16, and that is the name, that is for the water saturation. Then you can do the same for relative permeability. And you can save the scheme and reuse it again and again in your subsequent project. But I'm going to use the scheme. So the scheme means that whatever you set up, you save it and you can reuse it subsequently. Now, here is the scheme for the oil water system for relative permeability. I'm just going to load it in Techlog, and that's all. So you can close the buffer. Then that is already in Techlog, as you can see here under the data set. So I'm going to also move the capillary pressure the same way. Just drop it in there. You set everything up, or if you have the scheme already set up, you can just load it. So for the purpose of this section, I'm just going to load the scheme to make it faster. So everything is set for me. I'm just going to load it again in Techlog. Lastly, I'm going to import for the gas oil system, the relative permeability. Then that is the end of the import. So the next thing that I would like to do thereafter will be to average and generate for the number of rock types that I have, eventually the saturation tables that I will need for my simulation. So that is done, but let's visualize at least what we have imported into Techlog. So I'm going to plot the relative permeability first. You can just drop and drag. That's the saturation to the x-axis, both up and down, because we want to plot on both sides of the y-axis. So I'm going to put the water relative permeability and the oil relative permeability on the other axis. So you can see this is the data that you just imported into Techlog. You can save your plots, definitely, and so that it will be saved under the cross plot, and we can double click to open it in the future if you need it. Next, let's just try to plot the capillary pressure as well, just to see before we move on to follow the workflow that I presented to you earlier. So I'm going to plot the capillary pressure on the Y and water saturation on the X. Now you have the capillary pressure data that you're going to use. So I'm going to use on the SCAL window, the rock type to table guided workflow. That's still on the top pane, but now under the guided workflow group. So I'm going to start with the rock type to table. So the saturation function table, that's what it means. So it's going to guide us through the workflow. When you open that, I'm going to remove the correction to the closure and the CBW correction to capillary pressures. I'm going to fill in my data. Just click on next. Then the capillary pressure data, just drop it in here. Automatically, it will detect your porosity, permeability. Same goes to the relative permeability for the oil water system. Next is to embark on the deterministic rock typing that we talked about. And at this point, you can select whatever method that is adequate for your data. And this is best done with your petrophysicist and the geomodeler, actually. The workflow is very easy to follow, as you can see. And here, I'm going to select my cutoff just to have 3 rock types. So I'm going to delete the rest. If you apply that, you're going to see the impact of what you've done immediately. So I'm going to have 3 rock types because I'm having 2 cutoffs. One for the very good sand up there. And I'm going to just move this to also have the medium sand and the poor sand, as the case may be. I mean, this is interpretive. Anybody can actually come up with their own interpretation. That is the end of the rock typing. So the next will be to average the capillary pressure. However, before averaging that, we want to make sure that we put everything in the same condition, right? So the lab condition, I want to take it to the reservoir condition. In the reservoir, imagine if you have the sigma reservoir, that is the interfacial tension, which is 30, and the cost of the contact angle, which is 1 in the reservoir. So I'm going to make sure that I have the same condition for my lab and reservoir, okay? I take it to the reservoir. Here is also where you set the cap that I was talking about for the maximum capillary pressure. So you will see the effect of that in a moment in the workshop. So you can see the relative permeability, the capillary pressure in the reservoir and the lab, they are currently not overlined because they are not in the same condition. But now putting them in the same condition, you see what happens. So the next thing is to define the maximum capillary pressure, which will be a reflection of the height above the free water level in your reservoir that you've got. So let's set the value there, and that is what we have. Next thing that you want to do here, normalization, I'm saying no. So I'm just going to average on X. Here you can see that you have the good sand and the average for the good sand because we have 3 rock types based on our rock typing. And you can see the medium sand and you can see the poor sand, right? And the average, as the case may be. Next is to do the relative permeability averaging. And here, if you notice, you can see the coded water saturation and you can see the critical water saturation. They're pretty the same, but you can adjust the value here. You can also adjust directly from the graph, or you can adjust on that table. But I just keep it for now to be the same. The final part is to set your how many nodes that you want and the precision, the decimal point that you want on the table. And here will be the final result for the 3 rock types that you've seen, the averaging that we've just done now. But this is for the oil water system. So that is the table. You can just open from the link and see the table that you've just generated for the 3 rock types. So that's the water oil system. If you have 3 phases in your reservoir, then you have to get average also for the gas. Then you have to associate the 3 phases together, or when I say the 3, that means that you're looking at the gas oil and the oil water. At this point, I already have the one for the gas oil system. So I'm going to go to table generation. And this is what we're going to use a lot today to generate the table. So I'm going to fill in the table generation variables. Then I will run it and it will generate the final table for me. So the first part of the table, the inputs that you need to drop, they're already part of what you have already averaged from the previous steps. So those average values are what you're going to be dropping in. For instance, the rock type, that defines the 3 rock types that we've got on the basis of we use Winland 35, you remember? So the next is the capillary pressure average that we've done, which is that. So we can just bring in the capillary pressure average. And the wetting phase saturation, which will be the average for the water saturation, SW normal average. So you can just drag and drop in the input just to let you see that here we're looking at the wetting phase saturation. So I'm just going to put it back. You can check what it is, and that will automatically reflect those three averaging that you have made to the capillary pressure. So what you want to do next is moving on to the relative permeability for the gas oil system. Let's drop the group for the relative permeability of water first. So the group again is petrol rock type, and the saturation, the average, you need to drop the one that is the average, not the one from the lab anymore. We're going to drop the wetting phase saturation, but the average one, that's just the 3-1. Then you're going to drop your RW, that's the relative permeability, water relative permeability, then the oil relative permeability, average, all average. Then same for the gas oil system, then we can just generate the table, and that will be the end of the workflow, the first workflow, actually. So let's go to the gas oil system, and we also had the average. The group again, same group. The gas saturation, the average, which is that, just moving. And again, the KRG average, KRG average. So we drop that as well, and KRO average. You can set what is the precision, how many nodes, select the type of family, and just run it. So now it's running and it's done. So let's bring the table that we've generated up so you can see where the table is saved, and you can just open the table, the gas oil and the oil water table now. So that is, you can see the SWOF and SGOF and 3 for each. And that is the end of the first technique that we want. I hope that is clear before we move on to the next one. So I'm going to be working with the same project throughout this section. Moving on to the second technique that we're talking about, here we will cover the situation where you might just have the endpoints of the flow properties from the conventional or routine co-analysis experiment. This is definitely not a showstopper for us because we have endpoints. We can still go ahead and generate the saturation function tables from this data. Just to give the background of some of the correlations that are available, the popular one is the Cori, and the Cori, of course, the creation or formation of the Cori will start with the normalized water saturation. And on the basis of the normalized water saturation, then we can generate the relative permeability. So the relative permeability to water, for instance, will be the endpoint relative permeability to water at the irreducible oil saturation multiplied by the normalized water saturation raised into power the exponent of the Cori water. And same goes to the oil. And we can actually put in the normalized water saturation. And that is the Cori correlation, basically. We're familiar with this. So we see how to generate this. It's just to give the background about the equation. So again, we also have the LET that you can use. So the derivation of the LET is pretty similar, except that the Cori exponent are now replaced by the LET for the oil and for the water. So this will allow smooth and flexible relative permeability curves. And the L part describes the shape of the lower part of the relative permeability curve, while the E part, of course, describes the intermediate height of the curve, and the T part would define the upper or the top part of the curve. I will just show how to do this in Techlog. We have a similar calculator in Petre that we can use, but in Techlog, the beauty of this is you can generate at the same time for multiple set of endpoints. Imagine if I have 5 endpoints. So I want to just generate, I mean, you can have the endpoint and just import into into Techlog, Well, I'm just going to take the ID into Techlog, then create the endpoint in Techlog. And then we generate the relative permeability from those endpoints. That's another workflow. You can just copy this. And if you copy that, what you can do is just import from the clipboard. Then what you see the data right in Techlog, right? The way you have it on Excel. We might want to set the properties from the property windows when we are importing data into Techlog. Import from line 2 because that is where data is. Variable name is on line 1, as you can see. And you can set the well name that you also want. Just open that, you will see the number of well, the names of all the wells in your project. You will see them there. So you can select which one is which one. Then you can enter the dataset name, whatever name you want to assign to the dataset that you are importing into Techlog. Then at this point, I'm just going to call it endpoint IDs. It looks like we are almost good to go. So you can say load to import buffer, but now there is a warning that I need to set the reference. So I can use those IDs as the reference. What I'm trying to do is I want to just use that ID to generate endpoints, 5 endpoints, and use Techlog to create those endpoints at the same time and convert all of them to relative permeability curves. So that you can do that for 100 set of relative permeability. It's pretty fast. And that is why the calculator here seems to be smarter than what we've got in Petre. Go to the toolbox under utility to get the default value. So what this Python script will do is to actually get the default values for this number of IDs that we want when we run it. So just go to run, and it's just going to extract the endpoints, both for the LET and for Cori. You will have everything generated there. So if you want to plot, you can see, it looks like they are all ready for you. You can, maybe because at this time, I don't need the LET, I want to focus on the Cori for now. So I can just have all the endpoints ready. Let's visualize the endpoint using the data editor. You can see it up there. Just highlight and drag them to data editor. Then you see all the default endpoints that we just requested now. So you can also put their query value, and this is all you need to generate the relative permeability curve. So you can go to relative permeability curve generation from the endpoints workflow. So once you select that again, Techlog guides you on what you need to put in. Once you launch the process, just drop the data sets. Pretty easy, right? We need to drop our KRO. So drop that there. We need the coordinates. So you can drop KRO for the lower end points. The SWL, you can drop it there. The critical endpoint, KROW, you can drop that there. SWCR, you can drop it there. Then KRWR, you have everything generated, so you can just drop them here. Bear in mind that these actually array, these variables, because they contain set of the endpoints, actually. So you have KRW and you have the SW for the highest endpoint. So again, for the Cori water exponents, you drop it there. And lastly, for the Cori oil, you drop that. Then it looks like we are good to go to generate the table. You can select the number of nodes that you want at this time. You can say that the table is actually ready because all the endpoints are the same. So it looks like we have a single curve, but it's actually the numbers that we have introduced. So what we can do is to bring some variations into this endpoint. Let's say, for instance, I can adjust directly from here. You don't have to go to Excel. So let's go to the SWL. The first one, we can make it 0.2, 0.22. Let's say 0.224, I guess. Then let's say the next one, 0.228. And we can do 0.32, something like this. The beauty of this is you can also write expression from the data editor in Techlog. So double click on that and select this and double click on it again. And you can write that the critical water saturation is equals to the coordinate water saturation multiplied by 1.12. Automatically, it will update this. And once this is done, you can save it. Right click and save, or you try to close it, then it will let you save. Then just run it again. And you have the relative permeability curves generated. And that is the second method. So now I've shown you if you have curves, you can do the averaging. The second one is to generate from the endpoint. So we're going to move on to the next one. Our next method will cover how to generate capillary pressure curve from saturation height model that you have from your petrophysicist. Again, coming back to the saturation height modeling, because many of us were familiar with this method when we do a lot of manipulations on Excel when we are creating the permeability bin and to generate this. But you can actually do everything directly in Techlog using the same saturation height model that has been prepared by your petrophysicist. The concept of the saturation height modeling is pretty straightforward because we're trying to model the capillary pressure curve that we have. We are actually trying to fit it. And we relate the parameters to the petrophysical parameters that we've got, as you can see here, then relate it to the distribution of the water in the reservoir, which gives you the water saturation. So from there, we can get the water saturation as a function of the irreducible water saturation, the entry pressure, and the N, which is the pore size distribution parameter. Each of these parameters, of course, we have the capillary pressure, which is also a function of the height above free water level, the density, and so on and so forth. But each of these three parameters that I've highlighted here, you can see that they are also functions of the petrophysical properties like porosity, permeability. So once you get each of these, then you can get your water saturation, and that is the saturation height model. From these, you can actually build your representation of the water distribution in your model, right? That is what we do. And there are so many modules that we use. For instance, the one on the screen is the Brooks scoring, right? We have lambda, you have FOMIA, you have J function. So these are different ones that are available in Techlog. Just to summarize what the saturation height modeling is all about and how we can generate the capillary pressure table for different permeability being at the other end, but doing everything together within the Techlog environment, okay? So if you look at the SW infinite, the reason why I don't call this SWIR is because this is actually the SW based on the models that we're using, whether Brooks Corey, and it's actually the point at which we have the asymptotic irreducible water saturation based on our curve, which might not actually be the true irreducible water saturation in our reservoir until we set the capping. That might not be. So this is the one we have without the capping, okay? But that is the one that the module depends on. And it's a function of, it could be a function of porosity, it could be a function of permeability, okay? Then we also have the entry pressure, which could also be a function of permeability. Then we have the N, then we have the capillary pressure. So what the petrophysicist will do for you to get the water saturation, what we call the saturation height model, is providing these parameters. And from this parameter, we get the water saturation, right? From the dynamic space or end, what you want to do is also to use the same set of parameters to recreate your tables, which you will use for initialization and for your subsequent dynamic model in the simulator. So your capillary pressure that you are trying to, you can actually express your capillary pressure as a function of the other parameters from this equation. So it's like you are expressing the capillary pressure as a function of all the other parameters. So that gives you this. If you look at that equation and you rearrange the equation in this way. So looking at this equation very closely, what you have is, imagine you have the water saturation, okay? We have the entry pressure. You can see all of them coming from here. And we have N. So the only thing that you need to specify is the range of the saturation. Then this automatically will give you the capillary pressure. And this is what we do on Excel. We try to come back to Excel and put this down. In order to initialize the module with this, we try to define the bin that we have and say, for this range of permeability, what is the average permeability there? Then we get the representative capillary pressure for that bin of permeability. And we do that for each rock type that we've got. We define the number of bins and we use this to calculate the capillary pressure for each bin. Then we use either Cori or LAT to calculate the relative permeability. And we're good to go, right? But we do most of this on spreadsheets. But now with Techlog, you can actually just do everything together. And that is what I'm going to show you in the workflow. In order to do this, like I said, you need the column for the water saturation, as well as some important endpoints here, like the endpoint of water saturation at the residual oil saturation, which is this value. You also need the residual oil saturation. You also need the exponent and so on and so forth. You have to get it from somewhere, right? Whether from the limited core samples that you have, or maybe from a regional data base of the SCAL data that you've got. And that will be the last one that we're actually going to show you, the last method, whereby you can actually find the values of these guys from different sources, okay, and use them. But at this point, I will assume that you know them from somewhere, okay, and we just put them in. Once you have them in, you can actually create the tables that you want, okay? Let's go through this, the whole steps. So I'm going to cover what the petrophysicist would normally do and how we're going to generate the table from there. So most of these steps that you will see first, they're just showing the creation of the saturation height model. You don't have to do that in principle. So I want to visualize my capillary pressure because I'm modeling the capillary pressure basically. So you can see, I feel like these curves are too sharp. If you like, you can resample. That is the beauty of using Techlog. So I can resample the capillary pressure. Like I said in the morning, you don't have to do that, but it's just up to you. So let's, if you click on this data set and you can go to the properties and say, okay, the resample will come with PC lab underscore resampled, water saturation lab underscore resampled. So that's what we just, and it's going to be placed under the data set that we're using. That is the capillary pressure water system data set. Once we click on apply, okay? So what I'm going to do, you see, by clicking on apply, now I have it. And if you plot it now, you can see it is resampled, but it's the same data basically. So you can use either of the two. It's just up to you. It's a matter of preference. Of course, there are some discussion around, okay, the impact that it may have on the result, but in a way it could be insignificant. So we open the core build module, which is the process for generating saturation height module. And we drop our data set, the capillary pressure data set. And I'm going to select the one for the resample, the core water saturation resample. So here, what you're looking at now is I'm seeing for the 3 rock types that I've defined, which is, I now have here, I'm looking at each module and the Brooks-Curry. I want to use Brooks-Curry. You can change the saturation height module that you want to use at this stage. For the first rock type, I want to change from the lab condition to the reservoir condition first. I remove the rock type so that everything can happen at the same time and I can do it faster. I change everything, fill in the value. If I'm happy with that, the next, now I've taken it to the same reservoir condition, then I can put my rock type back. So you can see the 3 of them. So I'm going to have different model for each rock type that we've got. You can also select the core build module. That is the saturation process, module process that you're doing. Set some important parameter. What do you want to display the reservoir pressure when you are modeling it? And some important parameter to force the data within the limit that you set here. So you can do that. Then you can just run the process. So what you see here now is the water saturation best fit that you are trying to model with your data and the best fit model. And you can see the capillary pressure model that you're actually trying to model. For each rock type that we have, the 3 rock types, they look very nice in this case to some extent. So let's see what is going to happen next. I may want to display it in terms of the height instead of the capillary pressure reservoir. And I can set the maximum height that I want, because this is showing that what I currently have is going to 10,000 meters. That is the last reality. But in the reservoir, we might say the height of our reservoir is something here. So we stop it there. So let's set apply the limits on the y-axis on the height. Then we can set the height and say 500, whatever, 200, 100, as the case may be. So you can run it. Your model is representing the height that you've indicated. For me, the rock type, the good sand, looks pretty good. But if you look at the other ones, it's almost like my irreducible is going to go to 0, at least negative, but we force it to 0 because it's not turning high. Whereas the reality of my reservoir shows that the height is somewhere at 500. Okay, this is the model, but you can look at the fit that we have. So what I'm going to do here, if you notice, all this will be done by your petrophysicist. So don't bother about so much of this. But what I'm trying to do now is to match it, change some parameters to really match it to reflect what I have in my reservoir. And if I'm happy with my module that I've got, I'm just going to lock everything. You can press Control D once you change the first one, or you can fill it down. So I'm going to do the same here, Control D, then it's going to fill it up. Very good. So now I'm going to save this. So for the good rock type, I'm going to call it the first one, rock type. I'm going to call it good sand. And the second one, I'm going to call it medium. And the last one, I'm going to call it poor sand, okay? All this, again, will be done by your petrophysicist. But now, where the connection comes in, the integration is, you are going to reuse this directly from Techlog. We've saved it. You are going to load it for your own beans and to just calculate it directly within the Techlog. So these are the equations that we need. So what I'm going to do now is to create my permeability bin. So I'm going to bring in the spreadsheets whereby for each rock type, I've defined the number of permeability bins that I'm going to be generating the relative permeability curve for. Again, what I'm about to do, you don't have to do that in the Excel. You can do it directly in Techlog, but just to show you. So I'm using the equation for the rock type to calculate the SWIF. Same goes to the second rock type. I can just copy the Excel format and put in the variable. Once I paste that, permeability, then I change that to the cell number or value, and that gives me what I'm looking for. And lastly, I can do the same for the next one. So let's just move a little bit further. So we just have that. Now that we have that, we're going to copy it and put it in the clipboard. So once you copy and say clipboard, then you're going to have the data that you're importing. You can set again similar, give it a data set name, similar workflow that we went through before. The well name, data import from line 2, the variable name on line 1, and you can preview it first. And once you preview, you can see, you can set which one is the reference, your ID, which shows that you're going to have about 20 data sets. Then you can set the unit of permeability and the unit of the SWIF. So I'm going to use VV, okay? Now, once we have the data imported, we can just get it into Techlog. Those are the spreadsheet that we want to actually, you can see now we have it in Techlog. So the next thing that we want to do is generate the relative permeability for these bins and generate the capillary pressure for this bin. The capillary pressure will be from the saturation height modeling. Then finally, we'll combine both the relative permeability and the capillary pressure to give our table. So it's a very, it's a lot of interaction, this particular one, but we do quite a lot too. Those of us that we use this workflow on Excel to do it, but it's pretty straightforward, and I'm sure this will be automated as we begin to use it more and more. So you want to reassign the family for each variable when needed, and the value of that is when you are dropping them into the Techlog processes, it will automatically pick them up. So if you don't set the family, then sometimes it might not want to pick them up automatically. Again, let's look at the data that we've imported on the data editor so you can see everything, the permeability, the rock type, the SWF. So I'm happy with that. I'm going to generate the endpoint for all this, okay? So in order to generate the endpoint, I go back to the toolbox under the utility group, and I'm going to use the same Python script that I used previously, and I'm going to drop this data set. What this is looking for is how many ID that you have, and it will populate them with the default endpoints. And you can change the default endpoints once you launch that to represent what you really want in your own reservoir. So you can see now, and it's going to generate for both Cori and LAT. You can close that. We're done with that. So what we want to do next is let's try to just change some of these endpoints. If you drop that VM, so I'm going to use my SWIF as my SWL, at least for now. That is not really the SWL, but it's a different story. I mentioned in the first section that myself and Olivia were just finalizing a paper on that. You will have access to that shortly. So here you can set expression like critical water saturation as related to the coordinate water saturation. Then the same thing you can do for the SWR. So I'm going to put SWR as a function of the critical water saturation. This might be coming from maybe the core data that you've got. You've done some correlation. Then you've seen the relationship between these parameters. Or can also be coming from the last method that we're going to show you, which is the parameter-based method after this particular technique, illustrating now. So let's say the expression is this. I mean, it could be coming from anywhere, so I won't bother much about that. But for now, let's press enter, and automatically it will update that. So now we have all the endpoints ready in Techlog. And once you have the endpoint ready, just save it. Then you can go to KR from the endpoints. That is, you can generate the relative permeability from the endpoints. Now we need to fill in the property like we've done before. So since you've seen that before, I might just want to skip. So once you fill everything in from the endpoint that you've generated, then you can run the process. And the moment you run the process, you automatically see the relative permeability curve. So that is ready for us. But here, this is not really the saturation height modeling. If you look at it very well, I've generated the relative permeability from the endpoints. But the real thing that we're trying to demo here is to generate the capillary pressure using those saturation height models that you already have from your petrophysicist. So let's go through that and see how that will be done now. In order to actually, if you want to look at different rock types, you can just drop it on the filter and filter it, the good sand, the medium, and the poor. So you can see how many of these stuff. I mean, this is just to show you some of the functionalities that we have in Techlog. My recommendation for anybody who wants to really use Techlog very well as a reservoir engineer is I take the fundamental Techlog fundamental course. That was exactly what I did. Then I can understand how to plot, how to import data. Then you'll be able to do most of this doing in Techlog if you have not been using Techlog before. Remember now that we have generated the relative permeability. That is what is inside the generated folder. We just want to generate the capillary pressure. But for us to generate the capillary pressure from the saturation height module, then we have to have at least the dummy capillary pressure and the dummy saturation corresponding to that. So since we brought in this data without making provision for that, I can just grab the capillary pressure from the previous data sets from the lab and just put it here. But when you run this process, it's going to overwrite the value in there. So just to let you know, that's what I'm about to do. So I'm going to take the lab sample. I'm just going to drag and drop into my data set just to have something like a dummy there. If you do that, is because they are not the same ID, so it needs to resample. And once you click on that, you have this. The moment you have this, then it's easier for you to go back to the reservoir and go to the core build module. And then you can drop that data set, then it will pick up everything automatically. And you're going to see, if you open the process now, you need water saturation, capillary, and you have everything here. So if you drop this into that process, the only difference from what we did before and what we are going to do now is you are not going to run the process using the default module, but you are going to load those modules that we save, and that will help to recalculate on the basis of each permeability bin. That will help you to calculate the capillary pressure for each permeability bin that you've got using those modules. So again, I'm just trying to make sure that I have everything in the same reservoir condition because I use the dummy, which is the lab. So it's still showing the lab condition. So I'm going to feed that in, but I'm going to load the module. So remember, I'm going to load the one that we modeled before, the poor good standard we saved. That is the one that will come from your petrophysicist. And you can see those ones are already locked because they are modules that we've already got it. So let's take all this to the reservoir condition. And once we take it to the reservoir condition, we can just launch it. So while taking it to reservoir condition, I can just fast forward a little bit of that. So now that you've taken that to the reservoir conditions, setting the parameter just similar to what we did, I just wanted to see. Remember, we loaded the data from the petrophysicist, and we're just going to run the process. And once you launch the process, what it's going to do is to actually generate for you. We are not fitting water saturation in this case, but you can see for the 3 rock types, those permeability bins, you can now see them here. Now, so you can see for the good sand, the middle sand, for each permeability bin now, we have the relative the capillary pressure generated for those permeability bins. So now it's almost like we're done. All we just need to do now is to combine the PC and the relative permeability curves together. Then we have the table that we're looking for. So pretty straightforward. In this particular exercise, I've spent time showing you how to create saturation height modeling, which you will not be doing, but just to let you see the connection between both of them. In reality, that will be in the project from your petrophysicist. You just have to create the table of your bin and generate it. So within a very short time, you will get all the relative permeability curve for the bins that you want. We are done with that. We go back to SCAL and we go to table generation because now we have the relative permeability, we have the capillary pressure curve. So we're just going to fill in everything like we've been seeing before. So we fill that in, and once we fill it in, we can it's the same process, the PC. The table generation is something you have to look at over and over. So we're dropping the data that we need now. And once we drop everything for the relative permeability and for the capillary pressure, you set which family you want to update and you just run it. And once you run that, you will see that the table will show you the parts where it is saved, and you scroll down, then you can see all the tables are ready for you. Okay, and that is second to the last one. So I'm going to go to the last one. Here, what we're looking at is we're trying to obtain the flow properties from the library or from the database of the SCAL lab experiments, okay? The flow properties like SOW or KROW and so on and so forth, and the exponents or the LET parameters, all these are what we're trying to get from the database. And the method that we are going to look at is based on this publication. And this publication actually based on the database in Norway, okay? And this request was made by a client, which we now have in Techlog. You have Python scripting that can do exactly what I'm about to explain to you here. There are numerous publications on, how to determine and properly understand the multiphase flow in the core plugs. But majority of these, they just focus on estimating flow properties from a single core flow experiment. But when it comes to combining the data from several experiments and take advantage of that to generate your saturation functions for full field application, we don't have so much of such data, paper or publications. What we have is some of them, they highlight the benefit. But this particular paper, actually show the way to do it. Because most of these flow properties, they are reservoir properties, they have some trends between them that they follow. So for instance, there are clear trends between saturation endpoint like SWI, SOR, and SORG, and also the curve shapes. So in this paper, the trend module for relative permeability parameter were developed, and this is driven by the physical understanding of the multiphase flow in the porous media, how the shape, the endpoint of the relative permeability curve should behave, with respect to the permeability, to the SWI, or the wettability. So for instance, you can see what we have here. Where is my cursor? SORW as a function of, we can see the trend, the relationship, and the same thing with KRWSOR at SOR versus the SWI. You can see the trend that is there. So what they are trying to do is the flow property from SCAL experiments, they try to parameterize that, then store them in the database. If you have any reservoir that you want to model and you don't have enough SCAL data, then you can go to the database, take advantage, get those endpoints from there, and use it to generate your relative permeability curve. And this is actually the workflow implemented in that publication. So the parameterization of these properties will actually end up driving getting those endpoints that we want and the generation of the saturation function table. So the method starts by verifying each SCAL experiment that you have by the core flow simulation using the pulse scale module. Then you look at parameterize the flow properties that you want, like the SOR, SORG, KR, and the shape parameters of this curves, right? So they store all these flow parameters in the SCAL database in Norway, including the experimental condition, which the good news is we have it now in Techlog, right? You can use those data. And there are georeferences with the depth, the well name, the condition, the porosity, so they have everything together. And the good thing is you can actually filter this database to get something that will be representative of your own scenario and take advantage and use. So at the end of the day, analyze each flow parameter as a function of maybe initial water saturation, porosity, or permeability. Then develop the trend module for each flow parameter. Then based on the underlying theory of wettability, we have to, read the paper, you will really appreciate what has been done in this case. So an example of the flow parameter, like in the LET correlation, trying to assign a model to each flow parameter that we've been talking about, like the SORW. So this is the expression, and this expression you can now, the relationship, the trend looks like this. Same with this, with respect to the irreducible water saturation, it looks like this. So what they do basically, and the other parameters as well, they got the trend. And what you do with your own data in reality is to filter down to what is representing your own situation, then feed the model to it. But you're not just fitting the model, you are also trying to capture the uncertainty, the spread in the data. So you have the base, the optimistic one, and the pessimistic one. And this is repeated for all the parameters that you did actually, because these flow parameters are already stored in the database. So once you do that, you can now generate the relative permeability curve for the full field simulation from there. And that gives you the spread and capture the uncertainties that might be available. So that brings me to the end of the parameter-based approach. So we'll just move on to the demo. So if you look at Techlog, I'm just going to close this. So we have this in, okay? And what you want to do is, let me just show you how to bring that in. Let's delete this. And I'm just going to load that into it quickly. Just let me locate the data and show you how to load it in. SCAL. I'm just opening the data of my system. So this is the data that I'm going to be loading in. It's like the database of what we've got already. So let's rename the name of the well and call it AL5. And let's just drop it into our petrel from the buffer, and that is that. So let's close this, and let's close this. Now, what you're going to see here is all the database that we have here. So the beauty of this workflow is you can just visualize what you've got. You can come here. Maybe let's use this to visualize it. You can take irreducible water saturation versus SOWR. So what I'm trying to do here is to fit a function to this. I can also show you the KRW. So just drop that there. So we want to fit the function to this. You can take advantage of Python. So just open this, open the workflow. And on the workflow, let's say we've got this. You can just say, go in here, core oil saturation, and open the workflow. So once you open this workflow, what you want to do is go back to your project browser and go back to your data, and you can just drop this data in. Once you drop the data in, you can run the process. That's the Python that will help you to fit the function into both SORW as a function of irreducible water saturation and KRW as a function of irreducible water saturation. So once you run it, you can see what happens here. I can just close this. Don't say. I can move this on top of this just to have some screen for myself. So this is the data that you are now trying to fit. So what is interesting here when you're trying to feed the data is that this is the one I wanted to actually close. But that is fine. Do you want to close? Yeah, just close it. It's very easy to quickly generate. So this is this. Just go back to the Python. Just right click and say open. And just put our data in, the core oil saturation, and say okay. Then what I'm going to do now, put the data in and just show you something really cool about this. Run the workflow, display it. Then what you want to do is to fit the parameter. To fit the parameter, you can come here, let's say for the SOWR. So you have that there. How do you fit the parameter for SORW? Let's say this is maybe your BO. You can change it, the parameter, and see the impact. You spend time to fit all this, okay? Once you fit this, maybe 0.8, you see they're moving, they're adjusting to it, maybe 5. You do that for that, you can go on, I mean, it's very easy to fit. Then you move on to this. Let's say that is KRW or fitting. You can just fit this, maybe 0.9, just play with those parameters. You see, You play with them until you get the fitting that you want. Let's say 2. Those are the parameters. Once you fill the parameter, what is really interesting here is to generate the relative permeability, because this is based on what you have in the database. You can now use this for your SOWR calculation and KRO calculation. So you can go on to endpoint to table workflow. So if you go on to the endpoint to table workflow, do you want to close that? Yes, don't save it. Don't save, just close. So let's open this. What you can now see is you come here and generate from the endpoint your relative permeability. And I'm using guided workflow, very easy. So drop the data set here. You put your data set here, and you want to do those parameters as a function of SWI. If you have them as a function of relative permeability, you can also do that, or porosity. So you move on, depending on what function you want to use, Cori or LET. Let's say LET, I can take that. What is really cool here is if I go to the next one, I can just generate my Cori or LET on the basis of these endpoints. But what is really nice in what you have done is you can actually copy this expression that you have fitted based on what you've got in the database. Like this, you can put it here, okay, before you run the process. Like your, let's say KRWR, you can just copy it from here. And you can also put it here, and you can use that to fit the function and generate the relative permeability. And that brings us to the end of these demo sections that I've planned for you for today. Because of our time, I will put the rest on the video, and you can watch them on the website later. So it's 8 o'clock already, and I want to make sure that we keep to the time going forward. I will consider this as the end of the presentation and the demo. Yeah. Let me check the chatting window if you have any question.
My question, will this be shared, this presentation?
Yes, we're going to, the recording is always there. We've not processed the last 3, so we're going to process that with this together and put another 4 on the link, so you can go to the link and check it out. Any other question, any clarification? I hope you've really enjoyed this, because this is really important. Most of the saturation functions that we have are very crappy. In fact, maybe 75% of the saturation functions that we use in reservoir modeling carries a lot of uncertainties. So modeling them very well might also reduce the level of the uncertainties that we have.
Another question.
Yeah.
Okay, in the absence of SCAL data, how does this compare with modeling from log curves?
Okay, so if you have log, for instance, let's say water saturation, I believe that you're looking at water saturation from the log, maybe from Archie.
Yes.
So which is based on the resistivity log calculation. This is not the recommended way to populate 3D module. It's a good way to have the log along the well bore. So along the well bore, we see the log because that is the actual measurement. And in the SHM workflow, that is actually used to validate your SHM. So the log one is a good way to calibrate your SHM module that you have built, okay? But not to use it for the 3D population with geostatistics. It's not going to give a good representation of the distribution of the behavior of water saturation in the reservoir. So SHM is usually, if you have the data to do it, because you require the capillary pressure to do it, then that would be a good way to go. Is that okay for you? Did I answer your question?
Okay, that's fine. Thank you.
Yeah. Charles, you're welcome. I say that you are raising up your hands. You can unmute yourself and speak out.
Okay, yeah. Thank you, Sam, for that presentation. Very
You're welcome,
interesting.
sir.
Yeah, though I'm not an expert user in Techlog, but I was struggling to follow. My interest was in the SHM method, which is the last method.
Yeah.
And if I follow you very well, I think the first thing we did in that method was to generate the capillary pressure, and then from there we now calculate water saturation, which we now use to calculate the retenability.
Yeah.
So is there any way to QC the water saturation that we calculate from using this method? How do you how do you QC it? How do you QC the water saturation? Is there
So the water saturation that you've calculated, a good way
yes.
to validate it is to use the webboard data, the logs. And that was connected to the last question. I mean, this is actually connected to the last question that I answered. If you have the calculation from Archie's equation, then because that is based on measurement, it's derived from your measurement directly, then you can plot them side by side, and but you can use that to validate your SHM module before you now use the equation to populate the entire module. So that is one way to validate your SHM module.
Now, I have a question, please.
Yeah. So, sorry, before you go on, Charles, is that okay for you? And if you have any question on it, touch base with me. Many reservoir engineers don't use Techlog. I understand that. So what you said is fair, Charles. The objective of this is I want reservoir engineers to start using Techlog. It's very easy to use. If you need any demo, any section, or any training, let me know. We have the training that can address it. At the same time, if you need maybe a quick section to take you through and get you started, just touch base with me. I will arrange that section and make sure you are able to use it to do your work. Okay, next question. Please, you can go ahead.
Yes, my question is regarding the version. I can see that you are using 2020. How about
Yes.
a lower version of maybe 2019? Do we have this car on it?
We have SCAL, but the most developed SCAL is in 2020.
Okay,
That will give you opportunity to execute all the workflows that I've shown you. There are many SCAL workflows that we can use, like the normalization one. I've not talked about it, but those ones that I've shown you, I can give you at least. I have the confidence that you can run all of them on 2020. 19, you might not be able to do everything. Okay? Yeah. Any other question? I can see one hand is up. I'm trying to know who is that.
It's my hand. This is Shola. So I have it's just a comment on someone who asked if you don't have SCAL data. If you have SCAL data in another field, you can actually carry that across using the capillary pressure model, because you're using the IFT, which is independent of your lab method or your reservoir fluid system, and modify it to your rock properties for your present field. So this is,
yeah. So Shola, that is a very good one. You see the last workflow that I was showing you based on the database, which is you were going to import all those data you've gathered over years, or maybe from analog from a nearby field. You can now fit a function, you can get the endpoint from there. If you have that and use that to generate your relative permeability, that is actually the objective of the last workflow, parameter-based. Or if you just have an endpoint from another field, then you can use the second workflow that I showed you. Just put those endpoints in and generate your relative permeability. Depending on how much data you have would determine the workflow that you're going to select. And based on the selection of your workflow, then you can just go ahead to generate your saturation function table that is required for your simulation. Shola, what do you think? Is that okay?
It's fine.
Thank you so much. Miguel, please unmute yourself and speak.
Hi, Samuel. Great presentation, by the way. No,
Thank you so much, sir.
I just wanna, leave you with a few words of thought, about the usage of the Techlog and the training session you say you can assist with. We, the folks here at the AMPG, are very much interested in that. I myself have no experience with using Techlog, but yeah, we are interested with that. Please let us know. Yeah.
Okay, please do me an email, then we will take it up from there. I will be more than happy to provide different means to get you started with Techlog. Techlog is very easy. I mean, anybody using Eclipse, using Petra should be able to use. Is straightforward because the way you move the data in, the way you visualize things is very easy. Coupled with the fact that you have a lot of reservoir engineering workflows that you can implement that people are not using. You do your fluid contact analysis, you do gradient analysis. There are quite a lot that you can do. But unfortunately, reservoir engineers, they have all these features that they can leverage, but they are underutilizing it probably because they've not been using it. So one of my objectives will be to get almost everybody to start using Techlog again in reservoir engineering domain.
Okay, thank you. I will send you the email.
Sure. Okay, if there is no other question at this time, one will say thank you so much for your time. Let me just see if I have. Oh, hello.
Hi, Sam. Mukazo is asking a question on the chat.
Yes. Okay, let me check that. I think this is the slide. 1 second. Let me just bring out the right slide and conclude. Then we bring it to an end. But let me see the. You need to mute and turn off camera for all. What is the question? Okay, good presentation.
No, the question is that the webinars, right? That the videos are not updated yet in the SSA YouTube channel.
Yes,
The videos
we're going to work on the videos. Please just give us sometimes, maybe before the next, no, it won't happen next week. Don't let me promise that. Next week, we're going to do it, but not before the presentation. After the presentation, you have the last 4 with this one loaded to the subsequent ones that we've got. So everybody can watch it later. Okay, good. So at this point, we'll just bring the presentation to a close. The conclusion, the SCAL data, we know is a critical input for reservoir modeling, and characterizing it very well is key, and Techlog is there to help. Today, we've shown 4 workflows: averaging curves, correlation approach, either using Cori or LAT, the binning one, and the parameter-based one. So taking advantage of what you have and Python scripting to generate fitting and use those correlations to generate relative permeability curves. We are going to have another section coming next week on model initialization. So everything that we've learned today would transit nicely into the initialization, how to actually take all this input data to do initialization very well. And once we finish the initialization, we move on to U&O workflow based, like sensitivity analysis or certainty, the optimization. Then we end up to show you what we have in the field development planning. At this point, I want to say thank you so much for your attendance. I'm really impressed. Seeing everybody showing interest, asking questions is a really good way to continue to engage together. Please, for the first 4 presentations that we had, the feedback is still there. Once you fill that feedback, I'm going to close that in the next 2 weeks and give another link for the subsequent ones. So please go in. If you have not put your feedback for the first few ones that we did, the first 4, it takes less than 4 or 5 minutes. Click on the link in your invite and help us to put that in. And stay safe and see you next week.
Thank you.
Thank you.
Thank you very much.
Thank you, sir.
Thank you,
Thank
Samuel.
you.
Thank you, Sam.
Thank you, sir.
Yeah, thank you, Sam.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you, everyone.
Okay, many thanks.
You're welcome.
Thank you.
You're welcome.
Thank you and bye-bye.
Thank you, and see you next week.
Thank you. Bye-bye.
Thank you. Bye.
Namaste.